Now we're going to do a two-dimensional case, and what we're going to invert is the Laplace's operator. So that's the one that's second derivative with respect to x plus the second derivative with respect to y. So that one is defined on a mesh of points, and an appropriate boundary condition would be to prescribe the value of the function around the boundary. And so we're going to show how to do that now. So let me go back to a 2D mesh of points. So nx is equal to 100 and y equals to 100. I'll put double the points. Lx is equal to 1 and y is equal to 2. So BDX is equal to I minus I west divided by dx, and BDY is I minus I south by dy, and then the gradient operator, gradient, is equal to the x derivative and the y derivative. So let's do BDX semicolon dy. So this will stack these two operators one above the other. So the matrix grad will be will not be square, will be a rectangular matrix, because it takes in a field and outputs two components, the x and the y components of the gradient in this 2D example. And so that's why it's going to be twice as, the columns will be twice as long as the rows. So let's run it to see what we get. M is equal to nx times ny. Maybe I could, yeah. Okay, clear all EG. Okay, and now size of grad and size of BDX. So the BDX takes in 20,000 inputs in this case and returns 20,000 outputs, but the grad operator takes in 20,000 inputs but returns 40,000, so twice as many because we have the x and the y components of the gradient. And now we can compute the divergence simply in the following way. dv is minus the gradient transpose. So this is comes from the idea of integrating by parts. We can show that the divergence operator is minus the gradient transposed. So this works in general, works in spherical coordinates also. So we're going to use this trick to get the div and the grad operator. And then finally the del squared operator is the divergence of the gradient. So now we're going to test our del2 operator, or the inverse of the del2 operator, by constructing a function which is the analytical expression for applying the Laplacian to it. So we'll pick a function, and for simplicity, we're going to make sure that this is a function that's zero all around the boundary. That way, when we want to make our del2 operator differentiable, we can replace it by prescribed values on the boundary, and those values are all going to be zero, so it'll be easy to set those values. So the first step is to construct this function. So f is equal to, and we want a function here, remember, that is zero on the boundary. So an easy way to do that is to pick polynomials. So to make sure that it's zero at x equals 0, I will pick one factor, which is, for example, x squared, that is 0 on the boundary. And then I'll multiply that by another function, which is, that's 0 on the eastern boundary. I'll pick a function that's 0 on the western boundary, so x minus lx. Which I'll just pick it linear this time. And then we can multiply by a function which is 0 at the southern boundary. And then finally a function that's 0 at the northern boundary. And just for variety, to make things straightforward, I'll multiply this by a sine function of 2 star pi star y divided by ly. So this function, sine of 0 is 0, so it's 0 at y equals 0. And sine of 2 pi is 0, so the function is also 0 at y equals ly. So now we have a function which is 0 all around the edge. Let's test it. E.g., contour f, figure 1. Okay, so this is a function which is 0 all around the edges by construction. And so we want to compute the Laplacian of this to make a right-hand side for when we invert the Laplace operator. So the next step is to compute the Laplacian. Now, taking the derivative of this is not too hard, just a matter of repeated application of the chain rule. But to show you a new trick in MATLAB, we're going to take the derivative of this using MATLAB's symbolic toolbox. So to do this, I need to redefine the variables x and y, because right now there are these big arrays from the output of the mesh grid. We wanted to redefine them as symbolic variables. So the way to do this is to first clear these variables x, y, lx, and ly, and then define them as symbolic x, y, lx, and ly. And now f is now a symbolic expression, so it's no longer an array of numbers the way it was when I contoured it. So we can see that if I run it, e.g. And now f is now this expression. Whereas before, if I didn't do this, if I didn't define it as symbolic and I run it again, clear all, e.g. Now f is a giant array. Alright, so we want to make it symbolic. And now we can calculate the right-hand side symbolically using the symbolic capabilities of MATLAB. So diff f x comma x, this will be two derivatives of f with respect to x, plus diff f two derivative with respect to y. Alright, so if I run this, and then I look at what rho is, rho now is this expression. There's also a simplify capability, simplify this, and that will maybe shorten the expression a little bit. Rho, a little bit. Alright, so now I'll cut this, paste it in here, and comment out the symbolic calculations. Rho. I don't need those. And now I have the right-hand side. The only thing I have to make sure is that when I multiply, I do element-wise multiplication. Remember, x and y now are arrays again because I commented out these values. So I need to do element-wise multiplication by changing the star with a dot star inside here. These are scalars, so that's okay. These are scalars. This one is x cubed, so I want to do element-wise cubing, cube each element in turn, not multiply the matrix by itself 3 times. And then here also an x squared, and then the rest are all scalars, so I think that works. Let's try it out. E.g. contour f, remember f is this, and then if I apply the Laplacian to that, I should get rho, contour f rho. Yes, I get that. So we can test it. Alright, so first the function, figure 1, contour f of f. Alright, this is the function. Now the Laplacian of this function in figure 2, contour f of rho. Alright, so this is the Laplacian of this function. And we can also test our differential operator numerically by differentiating this function, the top one, to see if we get the bottom one. So rho numerical is equal to del 2 times f colon, and in figure 3 I will contour that. Contour f of rho numerical. One extra step. Remember, I have to define the size of rho n, zeros and y and x, and then I go back to here and I assign those as a vector. And now I'm ready to contour figure 3. And this looks nothing like that. And the reason is that this function is really this one, except on the boundary, because my derivative operator thinks that the function it operates on is a periodic function, and this function is not periodic, right? The top is not periodic, so when I differentiate it, I get this in the interior, but not on the boundaries, because now I'm doing finite differences assuming periodicity. So to show you that this pattern that doesn't look anything like the left-hand pattern, doesn't look anything like the the right pattern that doesn't look anything like the left pattern, that in fact they are very similar, is to recontour it, but now leave out the boundary edge, the boundary or edge points. So I'll plot from point 2 to n minus 1, and from point 2 to n minus 1. And I need to close the parenthesis. Okay, so this looks a lot like that. Okay, but that's not the problem. We're not trying to show that our del2 is a valid forward operator. We want to show how to construct an inverse operator. So for this, we need to modify our del2 to make it invertible by eliminating all the rows of my operator that correspond to boundary points and replacing them with ones on the diagonal elements. Right, remember my del2 is not even correct on the boundary anyways. So we'll just remove all those points and we will replace it by the identity, as I was saying. And then on the right hand side, we will replace those rows in the right hand side vector with zeros, because we want the inverted operator to return a function that is 0 on the boundary. So look, the size of del2 is big. It's a 20,000 by 20,000 array. We could do some index arithmetic or gymnastics and find out what is the index of all the boundary points. An easy way to do that is to use MATLAB's find function. So I'll show you how to do that. Close all. So I'm going to make a boundary array. B is equal to zeros, and y and x. And then I'm going to replace the boundary points of b by 1s, and then find those points. So b of 1 comma end equals 1. So this will set the southern and northern boundaries of b to 1. The rest is 0. And b colon comma 1 comma end. This will set the eastern and western boundaries of b to 1. So to show you that this will work, let me make this to be a small array. 4 comma, let's say 7. And bg, b. So you see now b is 1 all the way around the edge. And now if I find b, like this, I get a series of indices which correspond to the indices where b is 0. So I'll count them off and you can check that these are indeed the correct indices. So 0.1, 2, 3, 4, 5, 6, 7, 8. So the first 8 indices are all 1s. Then we skip up to 14. So 8, 9 is not a boundary, 10, 11, 12, 13 are not boundaries, but now 14 is a boundary again. 15 is a boundary point, and you see, oops, 14 and 15 are boundary. Then we skip some, 16, 17, 18, 19, 20, and then 21 is a boundary point. And 20, 22 all the way up to 28 are all boundary points. So this is a quick and easy way of identifying the rows of the operator that correspond to points on the boundary of the domain. So that's, we'll use this capability. So let's go back to 100 by 200 and then find the boundary indices. So ID is find B colon. So remember, B colon turns it into a big long column vector, and IB is all these indices of this big long column. Okay, so find the indices of the boundary points. And then I will take my del2 operator, 2 of IB colon, and set all those rows to 0. And then del2 of IB comma IB will be equal to spy length of IB. And this will replace all the diagonal elements in the rows that are boundary with a 1, only in the diagonal, on the main diagonal. All the other ones will remain 0. And by doing this, we're essentially prescribing the value of those points. And we're prescribing it by assigning on the right-hand side vector the value we want it to be when we invert it. So this then means, before we do the inversion, we create a right-hand side vector, which is just row. And then the right-hand side at the boundary is not rho because our equations now have just a 1. So what we want to put now are the boundary values. And in this case, we make them to be 0. And now we can invert our operator. So f numerical is equal to del 2 backslash right hand side into a vector. And these parentheses. And now this function f numerical, which is obtained by inverting the Laplacian, should match or the way we define f up here. This one up here is really f analytical. And so let's plot these and compare them. So figure 1, subplot 1/2, 1, 1, contour f, x, y, f analytical, color bar, set GCA font. So fn is equal to zeros and y and x, and then I assign it to the column. So f of n will keep, when I reassign the values in here, when I populate fn, it will inherit the original shape of f. And so that's an easy way to make it back into a 2D array in the proper order. So e.g., and then my function is here. Let's stretch it. So the top one is the analytical, the bottom one is the numerical. They look very similar. We can maybe contour the difference. So CLF, contour f, x, y, f analytical minus f numerical, color bar, set, GCA, font size. So this is the error, and you see here it's 10 to the minus 6, and the range is from -5 to 5, but the original function is much bigger than that. It is of order 0.1 to -0.1, and the error was already 10 to the minus 6. Now, in the construction of this gradient over here, this gradient is constructed with backward differences, so these are first order operators. So we would expect, if we apply the gradient, that the error should decrease linearly with the mesh refinement. However, in this case we have two operators. We have the gradient and the divergence. And the way we've constructed the divergence, we have a Laplacian here, which when we multiply div times grad, which becomes a second order approximation to the Laplacian. That means that we expect the errors to decrease quadratically as we refine the mesh. And to demonstrate that this is indeed the case, we will start off with a very coarse mesh with only 10 points, and we will evaluate the errors once we increase the resolution by a factor of 10 to show that the errors should decrease by a factor of 100, not a factor of 10. So the first run times through, e.g., CLF and contour the error. Alright, so this is the error, and it's of order 10 to the minus 4, the error over here. Now we will multiply the number of grid points by 10. So in other words, refine the mesh by a factor of 10, decrease dx and dy by a factor of 10, so it'll be 10 times smaller. So our error, which is 10 to the minus 4, should go to 10 to the minus 6 now. That's the prediction. Let's try it. Clear all G. So, and now contour F. And the error now, I don't know why sometimes it puts the 10 to the minus 4 on top and sometimes on the bottom. But anyways, now the error is of order 10 to the minus 6. And I don't know if the computer has enough memory to go up to 1,000. So now I have a mesh of 1,000 by 2,000 points. Probably my computer will run out of memory, but let's give it a whirl. The prediction is that the error should go down to 10 to the minus 8 now. So let's see. clear all, EG, and get ready for a long wait. The fan of my computer to start spinning. This is a giant matrix. So the array del2 is going to be 2 million by 2 million. So I have 2 million equations in 2 million unknowns, the linear system. It's already done. So much for taking a long time. And here's the error. Oops, CLF. Here's the error. And now it is indeed 10 to the minus 8. And so this is indeed a quadratically second order differential operator, a second order invertible differential operator because we prescribed the value on the boundary. If the value wasn't 0 on the boundary, we could easily change it. For example, if I change my original function and add a plus 10 here, plus 10, now the boundary value will be 10, right? It used to be 0, now it's 10. The Laplacian will just kill this 10, so the right-hand side is the same. So when I do the inversion here, the right-hand side boundary value, I now want to set it to 10. And if I run this, now I'll have a function that is 10 on the boundary. So let's run it. Clear all G. Now that I know I can invert Laplacian on a mesh of 2,000 by 1,000 points. All right, let's look at the error or the functions. This is the top is the analytical and the bottom is the numerical. Both are 10 on the boundary, right? The 10 is around here. I think that's the boundary value. We can look at f analytical of 1, 1. It's 10, and f numerical of 1, 1 is also 10. In fact, all the edge points are all 10 by construction, both the numerical and the analytical. All right, so this is how we construct an invertible differential operator.